we'll continue on here. We left off talking about golden section search, and we didn't finish that up, right? So I'll just kind of quickly go over golden section search, and we'll call this L and R, and then we've got to spot A and B, and I don't know how they're labeled in the code, but or whatever. But the idea is we evaluate all of these points, and we've got these two midpoints where B is, basically 0.618 of the way to R, and then A is 0.618 of the way to L. And so that would be, if L was at 0, L equals 0, and R is equal to 1, then A would be at 0.382, and B would be at 0.618, right? If we had it set it that way. And then we evaluate f of A and f of B. And if f of A is less than f of B, then L, A, and B form a set of 3 points where we know a local minimum has to exist. Has to exist, right? Because we said if you've got two endpoints and they're both bigger than A, because the other implication is that f of A is also less than L, or f of L, then we know that a local min has to exist between L and B. Okay, and so what this allows us to do is we are going to just remove this section, and now we have now we will check for a local minimum on the interval L to B. Okay, so next iteration, so we will search for a local min on the interval L. Oops. What just happened? Okay, L to B. All right, I don't know, something. All right. All right, and this is where the golden section comes in, right? So I'm going to go to, I'm going to flip to the next slide. All right, so here, so if I go L and B, and we had A, right? L is at 0, B is at 0.618, and A was at 0. What did I say? 382, something like that, something around there. Okay, and our function looks something like this now. Okay, well, we are going to rename. This will be our new interval. I'm going to use my. Okay, so L will remain L, B will become the new R, and what do we know? That this this location, this is 0.618 of the way to R. Okay, so this location 0.382 is the golden ratio of the way up to R. So we can just reuse A, but this will become the new B, and then now we must find a new A location. Okay, so at each iteration, we don't have to recalculate two midpoints. We reuse one of them, and we just calculate one new midpoint. Okay, so so at each iteration, we do not need to calculate f of A and f of B. Okay, we can recycle one of the old points. So this is why we use the golden ratio. Is that a question over there?
Yeah.
Yeah.
I think you said this last class, but L and R doesn't always have to be 0 and 1.
Correct, correct. Just for illustrative purposes, I'm using 0 and 1 just so you can see that it goes, 0.618 of the way. But yeah, if L was at 0.17 and R was at 85, that establishes it, and you're just going, golden ratio of the way from one end to the other. Okay, so we can recycle one of the points and its corresponding f. Okay, which is beneficial because sometimes calculating the value of the function at a certain point could be computationally expensive. Like there might be a bunch of operations, and I don't know, maybe having to calculate this could take a while. So so we do that, and we just continue to iterate, and at each iteration we are shrinking, our interval that we are searching over just shrinks by about 38% each time, okay, at every interval. And so it gets smaller and smaller and smaller and smaller until at some point, you are searching at some very small place, and you just say, okay, we will pretend like it has converged. Okay. And like the bisection method, golden section search is guaranteed to work as long as you have a function where you have just one a single local min in the interval. Okay, we can recycle one of the points and its corresponding f. Okay, and then we continue to iterate until the distance between L and R is less than some tolerance amount. Okay, that's a golden section search. So we covered unidimensional optimization with all of those as extensions of the root finding methods applied to derivatives. And then now we have a strictly numeric method. Requires no derivatives. We have the golden section search. Bless you. And okay, and then now we'll take a look at coordinate descent. Okay, and so this will be a multi-dimensional optimization algorithm. Multi-dimensional optimization, and so we'll just start off with kind of the two-dimensional case first, but it can be extended to n dimensions. Okay, so we'll begin with a 2D function. And this could be used for linear regression, right? So an application is linear regression. Now, linear regression has already been solved, so we probably would not do this. But with linear regression, how many parameters do we have to estimate? 2, right? What are those parameters? Yeah, we got, do we write B0 and B1? Okay, or beta 1. All right, so this would be the intercept, and this would be the slope, right? Okay, so let's say we've got, okay, so we got 1, 2, 3, 4, and not 2, 4, 6, 8, but 2, 6, 4, 8. Okay, and we want to find, what is the intercept and slope of the line that minimizes the squared residuals, right? So our sum of squares residuals will be the sum between y minus y hat squared. Okay, and so what this will be for our 4 points will be, the first one is going to be 2 minus, and we're going to have B0 plus, so we have y hat is equal to beta 0 plus beta 1x, right? So, sorry, this will be a tiny bit tedious, and this is why I only picked 4 data points. But here I've got beta 0 plus beta 1, and then we're going to have that squared, plus, and then I will have 6 minus beta 0 plus 2 beta 1, plus 4 minus beta 0. Can somebody type this into Wolfram Alpha for me? And then we'll have 8 minus beta 0 plus 4 beta 1 squared, right? So this is going to be our sum of squares residuals. Is that okay? Everybody? Nobody disagrees with me here. Okay. And then so now we want to find the value of beta 0 and beta 1 that will minimize this function here, right? So let's find beta 0 and beta 1 to minimize this. I don't know, is anybody able to simplify this? It would be nice if we can actually work with this. Sorry, I should have thought of this before. All right, let's just go. All right, so I'll call this intercept A. So I got 2 minus A plus B quantity squared, and then, all right, and then we'll, all right, what do I have? I got 2, 6, 4, and 8 and a plus 2b, a plus 3b, and a plus 4b. Does that look correct? It looks okay. All right, Wolfram, go. Result, see, yeah, this is exactly what we want. This isn't any simplified. Come on. Oh, here it is. Expanded form. Enlarge. No. Ah. Plain text? There we go. All right. No. Oh, dear. Oh, my life is so hard. All right. What did I do? Okay, so this is the function that we want to minimize. That's so small. Okay. Okay, let's work with this. All right. How do I don't know how to. Okay. All right. I'll just rewrite it bigger for you guys to see. Okay, so we got 4a squared plus 20ab minus 40a plus 30b squared minus 116b plus 120. Okay, this is our function of a and b. Okay, a being our intercept and b being my slope. Does it give me the yeah, 1 and 8/5? That's exactly correct. Okay, so so this is what we want to minimize. All right, so we've got this. We have, if you look at, if we were to make a contour plot, this is the worst line. Okay, we would have something that looks. Okay, something like that looks like this, okay? And this would be different values of A and different values of B, and we want to find this location here that minimizes the function. Okay, so how are we going to do this? Well, we start off at some initial point, all right? So this corresponds to the value of A and the value of B that minimizes the sum of squared residuals here. Okay, so how do we do this? Well, what we're going to do is we are going to just start at some arbitrary point, okay? And we're going to do a line search, meaning I'm going to set A to be constant. So at each step, first we will start with set A to some constant value. Okay. When I do that, then so f of A comma B given A equal to some, I'm going to just call this A0. We're going to set it to this, then just becomes a function of B, right? If I fix A to be a constant value, all of these things become constants. And then now I have a function of B, and I will just minimize B. Minimize the function with respect to B. So set A to some constant value, then minimize the function with respect to B. Okay, so in this case, let's just, for example, let's say our initial starting point for our data was that You might say like, oh, you know what? Let's start off with a equal to, the line is 2x, right? So in this case, a is equal to 0 and b is equal to 2, and this would, that might be a reasonable starting point if my data points are 1, 2, 3, 4, and 2, 6, 4, 8, right? Okay, so we start off with this, and if I say a is equal to 0 and b, we'll start off there, then f of a and b become, this is 0 plus 0 minus 0 plus 30b squared minus 116b plus 120, okay? So I have now the function of b is just 30b squared minus 116b plus 120, and we would minimize the function with respect to b. So 30b squared minus 116b plus 120. And let's just do this, because I can't be bothered to actually do this. 30b squared, what did I say? Minus 116b plus 120. Okay, and the what's the minimum value? The minimum value there is b at 29/15. Okay, so this is minimized at b equal to 29/15. Okay, so we go up to here and then we say, okay, this is where we have minimized b. Now that I've set b equal to some value, now I will do a line search in the other direction. Starting there, we come along and we set b to a constant. Okay, in this case, b is equal to 29/15. We use that value. And now we rewrite the function. So it is a function of a. Okay, and then we minimize with respect to a. Is that okay? All right, so I minimize with respect to a, and that's it. We iterate back and forth. So probably right here, if I plug in a into this thing, all right, if I plug in b as a constant and I plug in 29/15 to all of these things, I would get some number here, and I would get a function of a, and I don't know what that is off the top of my head, but now I have just a univariate. So at each step, we're setting the other variable to a constant, so our multi-dimensional function becomes just a unidimensional function. And we just iterate back and forth. So after that, you know, maybe I get something right here, and then we go the other way, and eventually I might come to the minimum here. Okay, and we would get some kind of stepwise path. So so here I have b equal to 29/15. I would plug this back in. Can I do this in R? In Wolfram Alpha. So wait, where did the expanded form go? Okay, so I've got plain text. Oh, it doesn't let me copy. Huh? B equal to 29/15. Does this work? Yeah, look at that. Okay, result 4a squared minus, you know, so here's the thing, 4a squared minus 4a over 3 plus 118 over 15. This is hard. Okay. So, okay, so with b equal to 29/15, then the function becomes 4a squared minus 4a over 3 plus 118 over 15. Okay, and then we'll go ahead and we'll check where is this minimized. Oh, I gotta write this. 4a squared minus, okay, of course we don't actually want to do this in real life, but 4a squared minus 4a over 3 plus 118 over 15. Okay. Okay, and then, and where's the minimum here? Where? A is equal to 1/6. Okay, so minimized at a equal to 1/6. All right, and then we go back to the original function. We plug in where a is equal to 1/6, and we get some version of b. Okay. 30b squared minus 338b over 3. I wish this let me copy it, but oh look, now this is copyable. Okay, so I take this, I copy this, and then we just kind of iterate back and forth, each time turning it into a unidimensional function that we optimize, and this gets me ever so slightly closer to so the global minimum is that b is equal to 169 over 90. Okay, I don't know what that is, but b is equal to 169 over 90, and our thing continues and continues, and then eventually it will come to a place, right, minimized. So we continue iterating, and then where it stops or where it converges will be the solution to our least squares regression problem. Okay, so we have a two-dimensional function searching over all possible values of slope and intercept, and we will find the slope and intercept values that minimize the sum of squared residuals. Okay, so at, I think it's going to be a equal to 1 and b equal to 1.6, we will obtain the minimum value of the sum of squared residuals, which is y minus y hat squared. Okay, so so just to kind of recap all of this, with coordinate descent, we have a multi-dimensional function. Okay. Each iteration has, we'll say, k substeps. K is equal to the dimensionality of the function. Okay, so set all variables except one to a constant value. So the function is now a function of one variable. Minimize the function with respect to the one chosen variable. Okay, and then at the kind of the next substep, okay, the next variable. So update all the constant values. Okay, use the new constant value. From previous step. Okay, and then and then again the function is the function. So we'll say we'll do a, and then the function is a function of one variable again. And then minimize, update, continue. So at each iteration, you're going to go through every single one of those variables. You've got to, you're going to set all of the other variables constant, so it becomes a function of just a, and then once you figure out what value of a you should use, then you update all of the other variables, or all of the other variables to constant values, and now you turn it into a function of b, and then you turn it into a function of c, and then so on and so forth until you go through every single one of your functions or variables, and that would be one complete iteration, and then you just start back at the beginning and you just keep looping through. So in your homework, I give you just a function of two variables. So first you're going to kind of set one variable to a constant. It's like you'll set x to a constant and you minimize with respect to y. Then you use that and you set y to that constant, minimize with respect to x. And then you just go back and forth. And effectively what it translates into is you are just searching in one kind of a single line here. So one way you can imagine this is if you've got a 2D function, you might have kind of this, you might have this, what is this, paraboloid, this shape here, okay? And basically at each iteration, you are going to just create a slice like this, okay? And then you say, all right, what does this thing look like? Well, when we trace it out on the, this is, I don't know, right? So we've sliced through the paraboloid right here, and so when we with y set to a constant, the now we just have a function that looks like this. We're going to minimize it right here, okay? And so we minimize it right there, and then that sets a new location for the thing. And so at the next iteration, we got this thing, and we said, okay, that was the location that minimized it, so we're going to come over here, and we're going to just run a slice and this direction. And this corresponds to, I don't know, something that looks like this now, right? And then again, you just minimize right there, and then you go back and forth, kind of just taking slices. So you're not looking at the entire bowl, you're just slicing it, so you just get a parabola at each thing, and you minimize the function there. Okay, so, well, I mean, that works for least squares regression, because with least squares regression, you got a quadratic way to look at the sum of squares. I don't know if this picture is any helpful. It makes sense in my brain, and but what I had in my brain looks better than what I drew up here, but I'm hoping this is at least, I don't know, halfway helpful here. Okay. So you will be asked to do this coordinate descent in your homework this week, and so if you have any questions, I'm happy to take your questions regarding this. Yes. Yeah, you keep going until probably you have a few options, right? You can just say, like, did my value of the function at kind of my current value of a and b, did that change much? And if it didn't change much, then you can say, well, maybe we've converged, and you can say that's we found the minimum or something like that. Yeah, so you'll probably want a tolerance level as well, okay? Or you can just say, you know, stop after so many iterations or something. Yes?
Would it also be valid to compare the, like, A-B pair that we get from the previous one? Like, if it has
Yeah, you can compute, like, the Euclidean distance from this AB to this AB, because what you might find is that you don't want to just do A versus A directly, or B. I mean, you can do what we call the Manhattan distance. That's fine, but probably you would do you know, your AB pair and then your next AB pair, and then check the Euclidean distance there. But if you want to, you could also do I guess Manhattan distance is just the absolute value change in A plus the absolute value change in B, and add those two together. And if those are less than some tolerance value, then that's also fine. Yeah. So, you know, on the order of 10 to the minus 6, 10 to the minus 5, I don't know. Depends how precise you want to get. Yes? Just the initial values? Yeah, the initial starting values, I wouldn't say random, but arbitrary. I mean, in some function, you might just kind of look at it and just say, all right, let's start here. But yeah, the thing about, you know, if you can start anywhere, and it should lead to at least a local minimum, okay? If you've got this wobbly surface, then it might not take you to the global minimum, okay? But with least squares regression, there's only one. The only minimum is the global minimum. Yeah, that's because it's a bowl that looks like this, right? So that's what we have. But yeah, you might have other functions that are a lot more, you know, have like 50 variables, and trying to minimize that is a lot scarier. If you guys take 102B with me next quarter, we'll look at gradient descent, which is multidimensional, and it takes a step at each thing. We're basically just taking the derivative and then taking a step in the derivative direction of the derivative. But I mean, so I think this is a good starting point, or at least to introduce us to the topic of optimization. Okay, and so so we'll start here. There's many other algorithms out there for optimizing. A fascinating one is the Noldor Mead algorithm, but I don't think we'll have time to cover it in our class. But it's worth checking out if you look up Noldor Mead and in your time. You want me to write that? Also check out, but not covered in our course. I don't know if there's an E after Mead. Noldor Mead, something like that. Okay, and that one's a strictly computational. No finding functions in terms of other variables. Okay, we'll end here. Have a great weekend, and we'll see you guys next week. Next week is Thanksgiving week, so it'll be short. Yeah. Okay.